Hello again, class. This is CIS 2353, and I'm your host, John Baugh. This is week 14. We will cover priority queues, which is chapter 13. If you are watching this in the year 2015, then you will note that Thanksgiving recess was last week. Hope everyone had a great week. The capstone project will be assigned this week as well, so keep a lookout. So let's get started on this. There's actually quite a few slides that we need to get through, but we won't go through all of these because much of it has an implementation which is part of a project inside of the book. So if you are very interested in the topics, the various data structures that you can store information in, such as priority queues and the Huffman encoding, which they talk about extensively, then you should fully implement it and make sure that you fully understand it. We will go through some of the examples they give and give a, so that we understand decently what a priority queue is, or a heap. So, and what the Huffman encoding does and how it makes use of a priority queue. But if you're heading towards, for example, further study at university, and you need to take a discrete mathematics course or an advanced data structures course, a more advanced data structures course, then I would highly recommend you look through the example and implement it and play around with it and make sure that you fully understand it. Priority queues are the topic of chapter 13. A priority queue is a collection in which the only element that can be removed is the highest priority element according to some method for comparing elements. So it is a variation of the queue that we've learned about before. A regular queue is a first in, first out data structure. The first in, first out data structure, as opposed to a stack, which is a last in, first out data structure. We covered those a little bit in tandem, actually. Before, but the priority queue is a special variation on the regular queue. Removals are not strictly on a first in, first out, or what we call, in some schemes they'll call first come, first serve basis. As examples, you have triage in an emergency room. If someone comes in with a splinter in their finger versus someone who cut their finger off, the person who cut their finger off is going to get priority even if they came in later. So same thing with things like heart attacks and strokes and things like that. Those are considered extremely high priority over someone with stomach flu or something like that. Although that may be painful, it's not life-threatening. So also severe pain, things like that. Kidney stones would probably take precedence over many other very painful things. So that's all I have to say about that. The thing that nurses do in this case, the nurse that's responsible or the coordinator that's responsible for the ER, is called triage. Okay, so the triage nurse is the one that kind of decides, who goes in first, even if they came in at a later time. So it has to do with severity. Other examples, air traffic control. There may be a queue of planes waiting to land, but the controller can move a plane to the front of the queue if the plane is, for example, low on fuel or has a sick passenger or pilot. So priority, the priority is established based on whatever needs are defined. So it's according to some method for comparing elements. So the triage nurse, the air traffic controller, all kinds of different ways to compare the different elements. Okay, in triage it would be the individuals coming in who are ill, in need of care. And air traffic controller would be planes. How do we compare them and decide on priority? So they give the example of the name, injury, ranking, and injury. So if we go here, we've got an 80-year-old with a sprained ankle, 45 with a broken leg, 80 with a sprained ankle, 20 with a broken neck. The question for triage would be, in what order should the patients be treated? So that would be, for example, the person with the broken neck would be in the most severe situation would probably get the treatment first. Then you have to decide between these. Well, broken leg would probably come next, and then if you have a tie, two 80-year-olds with sprained ankles, you would probably decide to give the person who arrived first, or who quote unquote has been waiting longer, the priority, even though they had the exact same condition. So at that point it becomes a regular queue for that particular injury. But there's many examples of priority queues in areas of such as scheduling and data compression, including JPEG encoding. So JPEG encoding does make use of priority queues. By default, the smallest valued element has a highest priority. We call that a min heap when we implement it, which we'll see in just a second. So that's as opposed to a max heap, which is used frequently when we do max heaps, and min heaps are actually used frequently in sorting when we start looking at the heap sort. Comparisons can be made by implementing the comparable interface or the comparator interface. So the Java collection framework's priority queue class does actually use a heap. However, it does have a flaw also. So what is a heap? We'll talk about the flaw in just a moment. Recall that a complete binary tree is full, except possibly at the lowest level where all the elements are as far to the left as possible. So a full binary tree, as we talked earlier, is one where each non-leaf node has two children. So that's basically the definition of the complete binary tree, all the way down to the bottom. So if something is a full tree, that means that, that's a full tree. A full tree is one where each node that's non-leaf has two children. Full binary tree. A complete binary tree is full except at the lowest level where all the elements are as far to the left as possible. So we would say that a full binary tree is complete, but not all complete binary trees are completely full, or what we would consider purely full. However, they're full up to the lowest level, and they're as far to the left as possible. A heap, T, okay, so we use this variable T to represent a heap. This is a complete binary tree such that either T is empty, so the tree itself is empty. We can say, oh, well, I guess it's a complete binary tree and a heap because it's empty. You can't really make any other statements about it. Such that either T is empty or the root element is the smallest element in T. This is for min heaps. For a max heap, it would be the largest. But for a min heap, the root element is the smallest element in the tree, according to some method for comparing elements. How do we define small? That's the next question. And then the left and right subtrees of T are heaps as well. So it's a recursively defined data structure, like all of our trees. So heaps ordered from top to bottom, but not from left to right. This is not a binary search tree. Okay, it's a binary tree, but it's not a binary search tree. You can see that this is not a full binary tree because 85, for example, does not have two children, and 36 being a lowest level leaf node, I probably should have said that, lowest level leaf node, does not have two children also. But this is a complete binary tree because it is down to the last level, the lowest level, as far to the left as possible. It is complete down to that level. So everything has two children down to this lowest level, which has the possibility of certain nodes not having two children, the level above it. But if this is the case, they have to be as far left as possible. For example, if 88 were on the other side, this would not be a complete binary tree. So again, a heap is not a binary search tree. With a binary search tree, you can look to the left and the right and know that the stuff on the left is less than and the stuff on the right is greater than. But here you'll note that with a heap, the smallest element is on top. The two elements below this element are both bigger, and then the two elements below that one and that one, they're both bigger than that element. So your children are always bigger than you in a min heap. For a max heap, they would always be smaller. As with any complete binary tree, a heap can be implemented with an array. The root element is at index 0, so we put 26 and then 26's children 40 and 31 in the next two. So 26 has 40 and 31. And then you have 40 has 48 and 50, and so on. Okay, so the root element's at 0, left child of the root's at 1, and so on. For the previous heap, we get this following array. As we saw in Chapter 9, when a complete binary tree is stored in an array, it is a constant time operation to go from parent index to child index, and from child index to parent index. In the priority queue class, which is part of the Java collections framework, null elements are not allowed. Here are the method specifications for two constructors and the three other essential methods. So this would be the default constructor, or what we call the no-arg constructor more appropriately. This is one that is a parameterized constructor. It has two parameters, the initial capacity and a comparator. The comparator is if you want to specify the way to compare the elements, other than natural ordering. The add method, the average time is constant to add, and the worst time is linear, as you can see here. Remove, it retrieves and removes the highest priority element of the priority queue object. And then you have element down here, retrieves but does not remove the highest priority element from the priority queue. The following run method will create a priority queue object and perform a few operations on the queue. For excitement, each element will be a string, and the unnatural ordering will be by the length of the string. So it's not the natural ordering which would compare them lexicographically. So by length would be a class that's defined elsewhere here. By length implements comparator. You'll notice that that defines a method named compare. Two strings, they're just saying if we set these two variables to the two different lengths, compare their lengths. If they're equal, otherwise return length 1 minus length 2. That will determine, it will return a negative number if I'm less than this one. If I, the string on the right, am less than this one, or the string on the left is less than this one, it will return a positive element, a positive number based on this, if this one is less than that one, right? Because if this one's 10 in length, this one's 5, it'll return a positive 5. Vice versa, and return a negative 5. So that gives us, that's what compare does. So what will the output be? If you think about the output, you would get, based on the length of these, then if you are ordering them this way, that the less length things come first, then you would say that no would come first, yes, well, yes and wow are the same, so then you would compare them lexicographically. Wow and yes, and then maybe. Fields in the priority queue class. There are some fields. Private transient object queue. There's a queue behind the scenes, so this uses it uses an array behind the scenes. This is the actual queue object. In case you're wondering what the transient keyword means, the transient keyword is basically a signal to the JVM that when serialization is performed, that the transient data should not be serialized. In other words, it's not intended to be the persistent data of the object, the queue in this case, if the object is serialized. Okay. So then what they're doing here, this is, I think they convoluted this a little bit. This kind of made me a little irritated. They convoluted this in that they're using the right shift operator here, and they are That's the left shift. They're convoluting this because they're trying to say that this is divide by 2. It's a quicker performance than using division, the actual division symbol. Well, this is multiply by 2, I guess, in this case. But if it were the right, it would be divide by 2. Right here, yeah. So, yeah, this is right. So this is basically divide by 2. That's the index here. That's how you would move up and get the index of your parent. Is basically you take the floor of the right shift. So the add method inserts the new element at the back of the array object Q, expands the array if it is full, and calls an auxiliary method sift up to restore the heap property. So to maintain that there is a heap property, that the thing is a heap, each element is above only elements that are smaller than it or bigger than it in the case of a min heap. This is our add right here. So suppose we're adding 30 to this following Q. You have to ask, well, where would it go first, and then how does it sift up? Well, the first thing it does is it goes as far left as possible, as low as possible, to maintain that it is a full Q. A full or a complete tree, rather, full down to the lowest level. So when you add 30 here, this is going to fall into place right here next to the 107. So the problem is that this is no longer a heap at this point. So in order to restore the heap property of this currently complete binary tree, but otherwise not a heap, you need to sift up. Okay, so the sift up operation means the element you just inserted, compare it to its parent, and then find its place, keep sifting up. So 30 to 48, the 48 will move down, the 30 will move up. And then since this is 32 is still bigger than 30, it'll sift there, so 30 will go there. And then 30 is bigger than 26, so it will stay there. That's exactly what happened. First move, it switches with the 48, swaps with the 48, then swaps with the 32. It would be inefficient to keep swapping 30 with its parent, so the sift up method simply moves the parent down until 30 is not less than the parent, and then the 30 is inserted at the child index. So 30 less than 48, move down. 30 is less than 32, move down. 30 not less than 26, so insert 30 as 26 left child. I believe, unless I'm just tired and reading it wrong, on page 562 in the Collins book, that there is an error. So if you are reading that, when it says because 28 is less than or equal to Q at 0, 28 is inserted at the Q, it should be 28 greater than or equal to, not less than or equal to. So that's at the top. I'm not sure if that's a reported errata or if it's just one that I figured out, but it's kind of it's not a real ancient book, but it's not a real new book either, so I figure that's probably reported. Remove, when you remove and you want to maintain the heap property, you do what's you use the sift down. So sift up is when you're inserting, sift down is when you're removing an element. So for example, if we call remove on this priority queue, the 26 will be saved. The 48 is stored at the queue location. So basically you take the most far right element, which is the 48, save the 26 elsewhere to be returned, put the 48 up here, and then again you have a problem just like with inserting. The 48, if the 48's up here and this is a min heap, 48 above 30 and 31 is just not going to work, so you need to sift it down back into place. So you, again, keep moving it down and swapping until you get everything where it belongs. So keep swapping 48 with the smaller of its children, notice the smaller of its children, until the heap property has been restored. So 48 gets swapped with the 30 because 30 and 31, the 30 smaller. Now it's going to swap with 32. And then since 48 is smaller than 107, then it just stays where it is. Okay, so you can work on the exercises. The compression techniques are one application of the priority queue, which I want to go through a little bit. For example, MP3, compared to CDs, MP3 files take up only about 10% as much space on disk. So they sharply reduce the time to transfer a song, for example, over the internet. There are variations on this. If you start with a CD of a song, then delete parts of the song based on the following. Some sounds cannot be heard by humans. Humans hear some sounds better than others. If a loud sound is playing, humans cannot hear a softer sound at that instant. The result is close to CD quality, but some information is lost, so the original CD cannot be recovered from the MP3 file. So we call MP3 lossy compression. So if you lose any kind of quality on the data, even though you get a reduction in the size, usually quite significant, but you also lose quality. Zip files, another thing. Keep trying to find larger and larger repeated patterns. Each such pattern becomes a dictionary entry, and the encoded file contains the number of the entry. So they start finding, they do an encoding here. So anytime, for example, they would find ask followed by something, they would put a 1. So 1 here. Not's never repeated, so we keep not there. So this is the ask not what your country can do for you, ask what you can do for your country. So any repetition, they can put the encoding scheme up here, and then put the encoding itself down here. This is what we call lossless compression. So it can find patterns and compress them, but it does not lose any data. So an application of priority queues are called Huffman codes. These are usually covered extensively in either in upper level data structures or discrete mathematics or discrete structures course at a university, possibly finite mathematics. So here's our problem. This is why we have the motivation to have Huffman codes. How do we compress a file without losing information? Compression saves space, and more importantly, saves time. So how can we do this compression but not lose information? In other words, we want lossless compression. So here's an example. Let M be some sort of message. Okay, it's just a variable representing some message we're sending, a letter, email, whatever, of size 100,000 characters. So it's got 100,000 characters in it, consisting of only the letters A, B, C, D, E. If we want to encode M into E, an encoded version, it's a sequence of bits. So it's similar to encryption, except the purpose is not for confidentiality so much as it is just trying to reduce the size of the file we're sending. In the Unicode collating sequence, 16 bits are allocated for each character. So if we use that encoding, there is no compression, and the size of E is 1,600,000 bits. You've got 1.6 megabits. Suppose that we use a fixed number of bits for each character. What is the minimum number of bits needed to encode 5 characters uniquely? So that's if we use a fixed number of bits. If each character is represented with the same number of bits, 3 bits per character are needed to encode 5 characters uniquely. And you might think, well, how did we arrive at that? When we're talking about bits, we're talking about binary digits. So that means that a digit at any given location within the number has to be either a 0 or a 1. To know how many items you can encode with a particular number of bits, you take 2 to some power. So 2 to the power 1, in other words 1 bit, that's only 2 possibilities. You have a 1 or a 0. So you can only encode 2 different values. If we take 2 to the power 2, that's 4. So that means we can encode 4 unique values. That's still not big enough to encode 5 characters, so now let's try 3 bits. 2 to the power 3 equals 8. It's more than enough of what we need for 5, so 3 for fixed size, 3 bits is the minimum number of bits that we need to encode the 5 characters. In general, Each encoding uses the same number of bits. The minimum number of bits needed to encode all n characters uniquely is the number of bits in the binary representation of n. The ceiling of log base 2 of n. Ceil returns the smallest integer greater than or equal to x. So this is, again, the reverse of the exponentiation I was doing. So if n is, say, 8, then we know that log base 2 of 8 is 3 because 2, our base, to the power of the result, 3, equals 8, which is n. So here's a possible encoding. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0. So, given our 100,000 characters with 3 bits, we have 300,000 bits. So 0.3 megabits. It's better, but it's not as good as we can do. So the question is, can we do better? We would like an encoding of n characters that does not require that many bits per character. In other words, not a fixed number of characters. So let's look here, see if this would work. Let's make A a 0, B a 1, C 2 zeros, D 0, 1, and E 1, 0. Okay, that could work, but do we have a problem? So it's way less than 300,000 bits if we were to encode the whole thing, but there's a huge problem. There's ambiguity. So if we have 0, 0, 1, 0, 1, 0, that could be an encoding of A, D, D, A, or C, E, E, or etc. So there's ambiguity here. So that's not it's not one-to-one, so it's not a good encoding. Some of the character encodings are prefixes of the others. So if we look back here, you'll note that A, which is a 0 encoding, is a prefix for C and D. So that's a problem. And then B is a 1, so that's a prefix for E. This is a big, big problem. So we can't use that encoding. Is there a way to avoid the ambiguity? So in order to do this, we have to come up with some sort of encoding where the prefix or the encoding of one character is not a prefix for another character. This is called a prefix-free encoding. If we can find a prefix-free encoding, it will be unambiguous. So the whole point here is to avoid using the minimum number of bits if we use fixed size. So the only way to do this is to use a prefix-free encoding. So we would get the lack of ambiguity, but also the benefit of being able to use a smaller number of bits for certain characters. So to get a prefix-free encoding, we create a binary tree. We consider left branches a 0-bit, right branch a 1-bit, and each character will be a leaf. So this is the coding that we get. So for example, C might be 0, 0, a B is 1, 1, D is 1, 0, an E would be 0, 1, 1, and an A would be 0, 1, 0. Since each character is a leaf, no two characters can be on the same path from the root, so this gives us a prefix-free and unambiguous encoding. So you have A, 0, 1, 0, B is 1, 1, C is 0, 0, D is 1, 0, and E is 0, 1, 1. Notice that none of these encodings, for example, B is 1, 1, none of these other encodings start with 1, 1. Now this one ends with 1, 1, but that's okay because its beginning or prefix is a 0. Same thing here. Nothing starts with 0, 0, so we're prefix-free here. Here's another binary tree that produces an unambiguous encoding. So it's a completely different one for that same thing, but you'll notice that it's a different encoding. Given an unambiguous encoding in E, to determine the size of E, we need to know the frequency of each character. In other words, these are two possible Huffman encodings, but which one's better? To make the compression as good as possible, we would want to see which of these characters, A, B, C, D, E, which one of them happens the most frequently in our document, in our message. So we would want that one to have the smaller encodings. For example, if B happens the most frequently, it would be great to have it right here, because then you can encode it with just a 1. It would be very easy. and it would be smaller. So because it occurs as much, so much, we want to reduce the number of bits to represent that code. To obtain a minimal prefix encoding, create a binary tree called a Huffman tree. That is actually based on the frequencies of the characters in M. So this is when we'll talk about that in a second. We'll see an example. At the level farthest from the root, okay, in other words, the farthest from the root level, we'll put the least frequently occurring characters. Their encodings will have the most bits, and that's okay because let's say we have in the English language an E, we wouldn't want to encode that with the most number of bits. We want to encode it with the least number. Okay, and then where an X or a Q maybe might be a lot lower in the tree, so it has more bits. Note that this is a variable length encoding, whereas the zip compression is fixed length. Okay, so keep that in mind. Suppose the frequencies are this. Left branch for least, right branch for next to least. So we take these frequencies. We look at the two least, so we've got A and C, correct? So we take A and C. 0, the 0 is the least, so that's, since 5,000 is less than 8,000, we put A on the left and C on the right. Now what? The sum of these frequencies is 13,000, so we make that the root of this particular tree. That sum is less than B's frequency of 20,000. So if we look at this, the 8 and the 5 make 13,000, and then if you compare that to 20,000, 8 and 5's combination, the A and the C, that combined frequency is less than B. So what they're saying is then we add B over here, and then you go up one level here. Okay, if you keep going, you'll eventually construct a tree that has all the characters in it. So D has the highest frequency, so it ends up as the element with the smallest encoding. So that's just a 0. Whereas an E would be a 1, 0, which is next highest, and then 1, 1, 1 for B, 1, 1, 0, A, and 1, 1, 0, 0 for A, 1, 1, 0, 1 for C. Right? So D, with most frequency, gets a 0. Notice these are prefix free, because nothing starts with 0. Nothing starts with 1, 0, except for the E, right? So there's no prefix. Nothing starts with 1, 1, 1. So this is perfect. This is a perfect encoding. This is a Huffman encoding. So uniquely, ACCEDED is encoded this way. Okay. So let's say we get a value and we want to know how do we decode it. So try to look through that and see if you can figure out how to do that. So 0, D, 1, 0, E, 1, 1, 0, 1, 1, 0. See, it's unique. Really, really interesting and really awesome topic. So you would be able to encrypt the whole thing in 206, or encode the whole thing, assuming that you have 5,000, the 20,000, 8,000, 40,000, and 27,000 from before, and then you say how many bits does it take to encode each of these, then we would multiply the frequency by the number of bits required. For example, the D, which had 40,000 occurrences in the document of 100,000 characters, only takes 1 bit. If it had taken 4 or something else, this would be much larger. But since it only takes 1 bit, that's only 40,000, where it could have been way bigger. So in total, we've got 206,000. So that's the size of the encoded values. So they then go on and show you how to do this using a priority queue ordered by frequencies to hold the elements. I'm not going to go through all the details in here, but I would recommend learning how are they actually going through here and do this. They want you to create a minimal prefix-free encoding for the following character frequencies, and then they actually implement a Huffman tree in the book, and I believe most of this is in the slides. As a couple theoretical parts, you should know what a greedy algorithm is. This is one in which locally optimal choices are made. Okay, it looks around and then sees what's most optimal. So sometimes, as with Huffman trees, greed succeeds. Locally optimal choices lead to a globally optimal solution, but this is not always the case. Keep that in mind if you go and take a more advanced algorithms course at university level. Not all greedy algorithms come up with what we call a globally optimal solution. Um, Specifically by repeatedly removing the two lowest frequently elements or combos of elements from the priority queue and then creating a subtree of the Huffman tree, you end up with a minimal encoding. So the 206,000 we saw earlier for bits up here, this is the smallest number of bits that can be used to encode it. So it's pretty cool. All right, so then anyway, they go through here and they go through the specification of the Huffman class. I'm, again, not going through the details, but I would recommend going through here, implementing it, make sure you're familiar with it. This won't be, you will have stuff possibly, you might have to do it by hand or know the basics of the methods of priority queues or Huffman encoding on the test, but I will tell you what you need at that point. I'm sorry, there's no final. Never mind. I'm lying. Um, sorry about that. Yeah, there's no final for this course, so I guess you don't need to worry about that. But I could add a component to your capstone that has to do with the Huffman encoding. So, all right. So that's pretty much all I have for you. If you have any questions, please feel free to email me. Read through the chapter. Make sure you're comfortable with the examples. If you have any questions about Huffman encoding or priority queues or heaps or anything like that, please feel free to email me. Thank you very much and have a great day.